Okay, this is lecture 4 in cam synthesis. We had seen the construction of the displacement diagram. We took the intake valve of an IC engine as an example. We saw various profiles for the displacement. We had simple harmonic motion, you had uniform motion, uniform acceleration, deceleration, and cycloidal profile. You could have other polynomial profiles also. Now, one of the issues with this simple harmonic motion we will see is that I have, when I look at the velocity and acceleration of the follower, I see the following things. What happens is that at these ends, you can see there is a jump. The red line is basically velocity. So you can see jump in velocity over here. It jumps from 0 to that value instantly. And then at the other end, I don't have an issue with the velocity. The velocity reaches 0 at the top side when we reach the maximum lift. But at the beginning, I have a jump. Now, if I look at the acceleration, at the beginning I have zero acceleration, even though I have a jump in velocity. But at the end of this, I have an acceleration negative, of course, in this particular, sorry, the acceleration reading is out here. So I have minus 200 whatever millimeter per radian square. So I have a fairly large deceleration, and then it is boom, it is brought down to zero instantly. So the same thing happens in the return. I start at this point, I have a jump in velocity when I start to move. And then, of course, as I reach the final 112.5 degrees, I go to zero velocity. There is continuity there. But I do have a discontinuity in the acceleration. So it is kind of the acceleration and velocity are continuous at some points, but discontinuous at other points. There are 4 points in the rise. We have the beginning of the rise, end of the rise, beginning of the return, end of the return. So in each of these quantities are continuous at two locations, but at other two locations they have jumps, and this is not a desirable thing. So such jumps are undesirable. So you have to ask yourself, why is this undesirable? So you think about it. So what if acceleration is going to be is a jump in acceleration or a jump in velocity? Okay. So I will leave you to think about this while I kind of say that look. I would rather have a follower motion with the continuity of lift as well as velocity and acceleration. So that means I demand not only the y of theta should be continuous, but at every point y prime of theta, which is the related to the velocity, and y double prime of theta, which is related to the acceleration, all of these to be uh, continuous. So what I'm going to propose is that I'm going to propose that there is a general equation for the intake. Of course, please remember I told you this at the beginning of last lecture also. I'm assuming that there are two dwells because I'm modeling an intake valve. It is very likely that you may have a cam follower mechanism where there is no dwell. There could be a single dwell and so on. So I'm not going to get into those cases. I'm looking at a valve design, and therefore I'm assuming that I have a rise followed by a dwell at the top position, and then I have a return followed by a dwell. So all these are marked here. 0 to theta I is the first rise period. Then theta I plus theta d, I would have the dwell period. Then from here to theta I plus theta d plus theta r, I'll have my second return period, and then finally from this point. So this is incorrect. So it should be um, theta I plus theta d. So this part has to be corrected then. Okay. The continuity of velocity and acceleration is imposed by asking the question that df1 by d theta. So this function f1 that I have, both at theta equal to 0 and theta equal to theta I should be 0. That ensures continuous velocity. Similarly, if I look at the second function, this is the continuity of velocity. Similarly, the continuity of velocity during rise, and this is the continuity of velocity during return. So we impose that. So these 2 points, so we are imposing 0 theta I, that is the beginning of the rise, end of the rise velocity should be 0, beginning of return, end of return velocity should be 0. So those 4 points we are demanding that. Similar demand we place on acceleration, which is the red part of the curve. So here we say that d square f1 by d theta square at theta I and 0 should be 0, and at these other return locations also it should be 0. So this is the continuity requirement, and of course the function itself has to be continuous at all these points. Now, I am going to assume that I could use for f1 and similarly for f2 a polynomial. We assume that it goes from 0 to 5 ck theta to the power of k. Now, the question is, why do we limit ourselves to 6 terms? The answer basically is the fact that we remember how many conditions we have. We have imposed basically, you saw 4 equations, the previous page, we saw 4 equations. So you had continuity of velocity, continuity of velocity for rise and return, acceleration similarly, so 4, and then you also have continuity of displacement. So effectively we have 6 conditions, therefore I can maximum I can solve for is 6 terms. So therefore we limit ourselves 6 continuity conditions and hence 6 terms. Now I am going to leave you to work this out at home and verify that if I plug in all these continuity conditions, the expression that I get for f1 of theta will look something like this. It is L into 10 into theta by theta I cube minus 15 into theta by theta I to the power of 4 plus 6 into theta by theta I to the power of 5. So this is the equation that I get. You can go ahead and plug in and see whether the velocity is continuous, the accelerations are continuous, etc., etc. Now, interestingly, the form for f2 of theta is very similar, except that it is L minus L into whatever that I have. This is referred to because you. So the interesting thing is that a polynomial which is basically going to be giving me continuous velocity and acceleration at the beginning and end of rise as well as beginning and end of return has the order 3, 4, and 5. It does not have a constant. It does constant, of course, we have in the in this case over here. It does not have a linear or a quadratic term, right? So this is called as a 3, 4, 5 curve because it has the power of 3, 4, and 5. So it's called a 3, 4, 5 curve. Now here is a plot of this. You can see from the previous thing itself that it looks fairly smooth, the rise and return. So you can see that the slopes essentially it reaches this nicely and then it takes off nicely and then seems to come down nicely. Okay, to convince ourselves, we are going to plot the velocities and accelerations. You can see that the red curve, which is velocity, I start at 0 velocity, which is what I should do. I reach a maximum velocity somewhere in the middle and then I start to slow down. The velocity comes back to 0. So I increase velocity, so that's an acceleration phase. And then the velocity starts to come down, which is a deceleration phase. But then I reach 0 velocity. I remain at dwell. Again, I start increasing velocity in the other direction, the return direction. Then I reach a maximum and then again I come back to 0. So this is kind of a mirror image, if you will. Because the rise and return that I have chosen are the same angles. So you can see the corresponding acceleration. The acceleration shoots up when it is somewhere in the middle over here, and then it decelerates so that I reach a maximum velocity. When will it happen? When acceleration is 0 here, I reach maximum velocity, and then I decelerate, and then effectively come back to rest here, right? So you can see it's more complicated. Accelerate, decelerate, and then again accelerate if you want to look at that. But basically you can see that from this curve that the velocity and acceleration is continuous. Now another motion profile that gives us a smooth curve. So you see the 3, 4, 5 polynomial curve gives us a smooth profile. Similarly, another motion profile that is smooth is based on cycloid. We already saw this in the graphical construction. The motion, cycloidal motion can be constructed from the fact that the acceleration basically is a sinusoid. So we assume that the acceleration can be written in this particular form, a, which is a naught some amplitude sine 2 pi into theta by theta I. So this is the acceleration of a cycloidal profile. So y double prime will behave like this. So theta I is of course the cam angle at which the rise ends. Now integrate to get velocity. So velocity will be c1 minus theta I by 2 pi into cos whatever expression. Now we want v of theta I to be 0, right? So that the end of the rise, I want the velocity to be 0. So we can plug that and get the value. So effectively, I now have an expression for velocity which looks like this, which satisfies the conditions at the beginning and end of the rise. You integrate this once more. you get the expression for y, and again we use the fact that at theta equal to 0, y equal to 0, which means that C2 is 0. So therefore, the expression for f1 of theta, which is this function, is now in this particular form. So you can see that there is a linear term and a sinusoidal term. So we looked at a uniform motion, which is purely linear, and we looked at a sinusoidal motion. Now we have a combination, which is basically a combination of linear as well as sinusoidal motion. Now the lift, of course, you can look at the lift is basically related. If I replace this, this will be L, which is a naught theta I square by 2 pi. Okay, now similar derivation can be done for the return portion, and if you look at the total profile, I'll get an equation which looks like this, and then you can plot this. This looks almost similar to what we have as far as the 345 curve is concerned. It's very similar to that. Again, the acceleration velocity profiles are very similar to the 345. Not surprising because we have ensured continuity at both ends. Now, okay, so this is as far as the follower motion is concerned. Now we move to the real deal. What do I do with this follower motion? So I have prescribed this follower motion. So I have a valve which I want to open in a certain duration using a certain profile, remain at that position for some time, then return, and then sit there for the rest of the cam rotation, right? So what is the cam profile which in contact with this follower will give me that kind of a motion? So we have to synthesize this cam. We assume that it is rotating anti-clockwise. You could, of course, do it if it is clockwise. It's not uh, a big deal. So we'll derive or we'll synthesize a cam assuming that it is rotating anti-clockwise. Please notice that if it is a symmetric cam, maybe we can get away by rotating that clockwise. But if it is an asymmetric cam, if it is designed to rotate anti-clockwise, if you rotate clockwise, you won't get the follower motion that you are supposed to get. All right, we are going to design first what I will call as a translating radial roller follower. This is what I'm going to design. I'm going to do this graphically first. In the later parts of this lectures, a few lectures down the line, we will look at how to do this using simple analytical. We'll derive the analytical equations. Then it is simply programming this in Excel or whatever. We don't have to go through the torture that I'm going to show you right now. Okay, but it is good to know because some of the principles involved in is what we will use in the analytical derivation also. So we saw earlier that in the CAM specifications that one of the primary design parameters is basically the base circle radius. This base circle determines the size of the CAM. If I make the base circle bigger, the overall CAM size becomes bigger, because remember, base circle is the smallest circle that is tangent to the CAM profile. Smallest circle drawn from the center of CAM rotation that is tangent to the CAM profile. Now we have to choose a roller radius. So I'm going to choose 5 mm. Therefore, the prime circle radius, which is the smallest circle that can be drawn tangent to the pitch curve, is RP, which is RB plus RR, which is 40 mm. So we have made these choices. Now we'll ask the question, how do we proceed? So this is, we want to synthesize this graphically, right? So the key idea, as you can see right through, when we were doing path generation, motion generation, again in CAM synthesis, the key theme that repeats in synthesis is the idea of kinematic inversion. So there too, we used the idea of kinematic inversion extensively in order to design the 4 bars for various features. Similarly here, in order to design the CAM, we are going to rely on the idea of kinematic inversion. So what do we mean by that? So we are going to say, see, the situation is that usually when you look from an observer in a fixed frame, the cam is rotating and the follower is translating. Now, if I ask the question, okay, imagine I'm going to sit on the cam. What does the follower motion look like? So I'm going to show you kind of an animation, and we will pay attention to the animation. You can see the follower. So of course there's a little bit of a jump here and there, but what do you notice? So the thing that you notice and is that if you notice the circle, what you notice is that in the inversion, the follower rotates clockwise about the cam center. So the cam is rotating anti-clockwise. So if I were sitting on the cam, the follower axis basically is going to rotate clockwise. So the follower translation axis is going to rotate clockwise about the cam center. And what you, of course, since it is a radial follower, the follower translation axis always passes through the cam center. But if you look at the follower sitting on the cam, you will see that the axis is rotating, but the follower is also translating along this. So you have a combination of what was purely a translation motion in the fixed frame, now has both rotation as well as translation along the axis. So we are going to use this philosophy to basically come up with the cam design. So I think I will stop here. I will have motivated you as to what is going to drive the graphical method of design. In the next lecture, we will go through this process. We will design this using the idea of kinematic inversion, and then we will design the cam. We will do this for the case that we have started off with is a radial follower. What if I have an offset follower? How do I radial? This is a radial roller follower. What if I have an offset roller follower? How do I go about the graphical design? We will take a look at that in the next lecture.